You've been sold the dream of star travel, but the physics says something far colder. The first humans to truly leave the solar system will not land on new worlds. They will die in deep space. In this video, you'll see why distance, radiation, failing hardware, and your own biology make that almost guaranteed, and why even knowing that. We might still decide to light the engines. In real space physics, leaving is not about passing Pluto. It's about stepping outside a gigantic, invisible structure the sun builds around you. That structure is what actually keeps some of the worst radiation away from Earth, and from your body. Right now, you live inside a huge magnetic bubble created by the sun. The sun throws out a constant flow of charged particles, the solar wind, and that flow drags the sun's magnetic field with it. Over billions of kilometers, that wind slows down and pushes against the thin gas between the stars. Where the push from the sun and the push from the galaxy balance, you get the rough edge of the bubble, the heliosphere. This bubble is big. It reaches maybe 120 to 150 astronomical units from the sun. 1 astronomical unit is the distance from Earth to the sun, about 150 million kilometers, or about 93 million miles. So the heliosphere extends something like 18 to 22 billion kilometers, around 11 to 14 billion miles, in every direction. Every planet, every asteroid we have visited, every crewed mission has been deep inside this one structure. The key point is simple and brutal. Inside the heliosphere, the sun's magnetic field and its outflow push away part of the most dangerous high-energy radiation that fills our galaxy. Outside it, that protection drops. So when you talk about leaving the solar system in a way that really matters for human survival, you're talking about leaving this bubble and stepping into raw interstellar space where the radiation is stronger and there is no natural backup. So if there is a bubble, where is the actual line, and how do you know when you have really crossed it? The answer is an invisible, thin but very real boundary called the heliopause. On one side, the solar wind is still flowing outward dominant. On the other side, the gas and magnetic fields that belong to the rest of the galaxy push harder than the sun does. There is no sharp wall, no bright ring. Instruments see a change in particle energies, directions, and magnetic field behavior, and that tells you have crossed from inside to outside. Voyager 1 is the first, and so far only, spacecraft to do this. It launched in 1977, used gravity assist from planets, and after about 35 years of travel it crossed the heliopause in 2012. Its speed is around 17 kilometers per second, about 38,000 miles per hour. That is faster than any human-carrying spacecraft we have ever flown. Even at that speed, it would still need tens of thousands of years to reach the nearest star. Now compare that to a future crewed ship. It must carry people, food, water, air, shielding, and complex systems. That makes it heavier, larger, and more vulnerable. You're not going to throw that kind of ship to speeds far beyond Voyager's with technology that looks anything like what we have now. You might think, fine, once you cross the heliopause, you are done with the solar system, but that is not how gravity works at these scales. So what are you really inside even after you pass this magnetic boundary? Beyond the heliopause, the sun's gravity still reaches out. Way past the planets, there is a huge, very diffuse cloud of icy bodies, the Oort cloud. It is not a flat disk like the planet's orbits. It is more like a rough sphere. Estimates say it may extend out to around 50,000, maybe even 100,000 astronomical units. That is getting close to 1 light year from the sun, meaning about 10 trillion kilometers, or roughly 6 trillion miles. The objects out there are mostly dormant comets, small icy bodies that only become visible if they fall inward. At Voyager's speed, moving through that whole region would take on the order of 1 million years. So even after a ship crosses the heliopause, it is still sitting deep inside the sun's gravitational zone. From a gravity point of view, you are not really gone. You are just very, very far out, still loosely bound to the same star you started from. At this stage, the scale alone should raise a hard question. How does human intuition cope with these numbers, when even light struggles with them? Light, moving at about 300,000 kilometers per second, roughly 186,000 miles per second, takes around 8 minutes to travel from the Sun to Earth. One astronomical unit. That feels almost instant. But the nearest star beyond the Sun, Proxima Centauri, is about 4.2 light-years away. In distance, that is around 40 trillion kilometers, or about 25 trillion miles. If you tried to cross that distance in a car, driving at 100 kilometers per hour, about 60 miles per hour, you would need something like 450 million years. That is longer than the time many major groups of life have existed on land. Our fastest probes, which we call fast in headlines, crawl compared to that scale. This mismatch between your everyday sense of distance and the actual structure of space is the core of the problem. And that brings you to the hardest truth in this first part of the story. Once you understand the real size of the heliosphere, the Oort cloud, and the gap to the next star, what happens to the first humans who actually leave this bubble? No propulsion system we have today, and none that we are close to building, can push a human crew to another star and let them arrive within a normal human lifespan, without extreme, probably deadly trade-offs in fuel, radiation, and engineering risk. If a mission launches in the near future, with technology that is only a few steps beyond where we are now, those first humans who cross the heliopause will not be settlers or colonists. They will be experimental crews on a one-way path, knowing that their lives will end somewhere in deep space, long before any destination starts to look like a place. The next question is simple and uncomfortable. How does your short human lifetime stack up against interstellar distances when you start doing the actual speed and time numbers? Your life has a hard cap, maybe 80 or 90 reasonably healthy years if everything goes well. Interstellar distances do not care about that number at all. And when you put both into the same calculation, the dream of getting to another star in one lifetime breaks very fast. Start with the nearest target, Proxima Centauri, about 4.2 light-years away, roughly 40 trillion kilometers, around 25 trillion miles, from our Sun. If you want to cross that distance in 80 years of travel time, not counting time on the launch pad or in orbit, you need an average speed of about 5% of the speed of light. That is around 15,000 kilometers per second, roughly 9.3 million miles per hour. That speed is not a bit faster than our current rockets. It is thousands of times faster than a jet airliner and hundreds of times faster than the fastest probes we have ever launched. To push a crewed ship weighing thousands of tons with fuel, life support and shielding to 5% of light speed, you are talking about energy on the scale of the total annual energy use of entire countries focused into one vehicle. Not once, but with enough margin for acceleration, deceleration and losses. That is why when people say we'll just go to another star, the keyword is just, because the raw numbers do not support that casual tone. So if the speed you need is that extreme, can you at least beat the system by just packing more fuel and firing longer, the way we do with big rockets now? The problem is, rockets work under a rule that gets cruel very quickly as you push for higher speeds. It is called the rocket equation, and in simple language it says this: the speed your rocket can reach depends on how fast it can throw exhaust out the back, and on how many times heavier it is at launch, compared to when the fuel is all gone. The higher the target speed, the more that mass ratio explodes. Chemical rockets, like the ones we use to get to orbit or send probes to Mars, throw their exhaust out at only a few kilometers per second. Around 4 kilometers per second is a typical figure, about 2.5 miles per second. With numbers like that, if you try to reach even 1% of light speed, about 3,000 kilometers per second, the rocket equation tells you that you needed an absurd amount of fuel, far beyond practical limits. Your ship becomes a flying fuel tank with a tiny, fragile crew compartment on top, and even then, it's probably not enough. Nuclear thermal rockets, which heat hydrogen using a reactor, can throw exhaust faster, maybe 2 or 3 times better than chemical. Ion drives and other electric engines can be far more efficient with fuel, but they trade that for very low thrust. They push gently for a long time. Even with these better systems, when you start asking for speeds that are a noticeable fraction of light speed, the same pattern returns. More and more of your mass must be fuel, and less is left for people, shielding and equipment. There is no trick wording that gets you around that basic trade-off. If pushing to higher speeds is so hard, maybe you think, fine, we accelerate more slowly, we stay comfortable, we use smart profiles. How does that part actually look when you factor in human bodies and g-forces? A human can stay comfortable at about 1 g, that is the acceleration you feel right now standing or sitting on Earth, about 9.8 meters per second. If you design a mission where the ship accelerates at 1 g for half the trip, then flips and decelerates at 1 g for the second half, the crew gets a normal gravity environment the whole way, which is good for health. But to reach 10% of light speed, about 30,000 kilometers per second, even at this constant 1 g, you need around 40 days of non-stop thrust to speed up, and another 40 days to slow down on the other side. That is more than 2.5 months total at full acceleration, with engines burning or being driven by some external beam the entire time. The amount of energy you have to feed into that system and the amount of propellant or power you need to carry or receive is enormous. And this is just to hit 10%, not even the 5% average over the whole trip we talked about earlier. So say you somehow solve the engineering and energy problem, and you do reach these high speeds with comfortable g-forces. What does that mean for your own aging? And for whether you arrive in time to actually do anything at the destination? Take a very optimistic case, you cruise at 10% of light speed, about 30,000 kilometers per second, around 18.6 million miles per hour for most of the journey. The bare travel time across 4.2 light years at that constant speed is at least 42 years. Then add the acceleration and deceleration phases, realistic mission planning and some margin, and you're easily pushing the total mission time toward 50 or 60 years. If you launch in your mid-20s and everything goes right, you arrive in your 70s or 80s after spending your entire adult life in one ship. Your body has aged, your systems have degraded, and you have maybe a few years at best to do real exploration before normal human biology catches up with you. And that is with a speed that is far beyond anything we know how to reach with crew and hardware that must keep working for decades. If the speed is lower, for example 5% of light, you are looking at travel times that are roughly double 80 to 100 years, which already overshoots a human lifetime. That means, by default, the mission becomes multi-generation, or you simply accept that nobody arrives alive. Those are not sci-fi edge cases. Those are what the basic distance and speed numbers give you, with no drama added. At this point you might try one last card, special relativity, and the idea that time can slow down for you if you move fast enough. Can this effect rescue you and let you skip ahead while everyone back home ages? Relativity does help, but not at the speeds we've been talking about so far. Time dilation, the slowing of time for a fast-moving traveller compared to someone at rest, only becomes strong when your speed is very close to light speed, not at 5 or 10%, but at 90%, 99% and higher. At 10% of light speed, the factor that tells you how much your time slows compared to Earth is only about 1.005. That means, if 50 years pass on Earth, about 49.75 years pass for you on the ship. You barely gain a few months. To get a really big effect, where decades pass on Earth but only a few years pass for you, you would need to accelerate to something like 90% of light speed or more. But pushing a crewed ship with shielding and life support to 90% of light speed takes energy that is not just a bit more than at 10%, it is many times more. Because as you approach light speed, each extra step in speed costs more and more energy. On top of that, the impact energy of even tiny dust grains and gas atoms in front of you rises sharply, turning the interstellar medium into a constant violent hazard. So in the realistic speed range where we can even imagine building something, time dilation does almost nothing for you. You age almost normally, you spend decades in the ship, and the star still does not come any closer than the basic math says. And this is all before you face the next set of limits, because even if you somehow accept the trip time, and the fuel and the speeds, you still have to keep a human body alive and mostly healthy for those same decades. Outside the sun's protective bubble, in a radiation environment no human has ever experienced. So what actually happens to your cells, your organs and your brain when you spend years in that invisible storm? How much protection do you think you really have between your body and deep space when you're not standing under an entire planet's atmosphere, but sitting inside a metal can a few centimeters thick? On Earth, There is a huge column of air above every square metre of ground, roughly 10 tons pressing down on you. That air, plus Earth's magnetic field, takes deadly high-energy particles from space and turns most of them into a low-level background, something your body can mostly handle over a lifetime. You do not feel it, you do not think about it, but you are inside a natural radiation bunker. Take that away, fly into deep space, and your atmosphere becomes a thin shell of aluminum or composite around your habitat, maybe 2 to 5 centimeters thick, a couple of inches. That is it. Instead of thousands of grams of shielding above each square centimeter of your body, you now have maybe a few grams, or less, in the direction of open space. There is no thick air to slow particles down, no global magnetic field wrapping you, just a local field if your ship can generate one, and some metal. In that situation, every high-energy particle that hits your hull matters. Many pass straight through without interacting, but when they do hit, they can break atoms, create showers of secondary particles, and slice through cells and DNA. The hull no longer turns a storm into a drizzle. The hull is more like a very thin umbrella in a hailstorm. It helps, but it does not change the nature of the environment outside. You have moved from a world where the radiation is filtered to one where it is mostly raw. So what exactly is hitting you out there? And how bad are the numbers when you measure them over years, not days? The main players are galactic cosmic rays and solar particles. Galactic cosmic rays, or GCRs, are mostly protons and heavier atomic nuclei, moving at speeds close to light speed. These are not gentle X-rays from a hospital machine. They carry huge amounts of energy per particle. Then you have solar storms, bursts of energetic particles from the sun during flares and coronal mass ejections, which can spike doses suddenly. We have hard data from the International Space Station and from probes sent toward Mars. In deep space conditions outside Earth's magnetic protection, instruments see radiation doses on the order of about 0.5 to 1 millisievert per day. A sievert is a unit that measures how much radiation energy your body absorbs, adjusted for how damaging it is biologically. For comparison, a typical chest CT scan in a hospital might give you around 7 millisieverts in one go. Now stretch that 0.5 to 1 millisievert per day over a long mission. In 1 year, that is roughly 180 to 360 millisieverts. In 5 years, 900 to 1,800 millisieverts, or 0.9 to 1.8 sieverts. That level is high enough to clearly increase your lifetime cancer risk, and to start damaging organs, especially if the dose is not smooth, but includes spikes from solar storms. And remember, this is still inside the heliosphere. An interstellar precursor mission lasting 5 years already pushes your body closer to serious limits. A true interstellar trip measured in decades would go far beyond that. If the raw environment is this harsh, maybe you try the obvious fix: add more shielding around the crew, pack the walls with dense material and let physics handle it. How far does that actually get you, once you put real numbers and mass into the picture? To cut down galactic cosmic ray exposure significantly, not just by a tiny fraction, you need substantial material in the way. Estimates say you might need tens of grams of shielding material for every square centimetre of surface if you want to reduce the dose by maybe half. That can mean tens of centimetres of water, or special plastics rich in hydrogen, or even thicker layers of metal. Hydrogen-rich materials work better than heavy metals for cosmic rays, but they still need to be thick. Think about a living area of 100 square metres, about 1,080 square feet, a small apartment's footprint. Wrap that in shielding thick enough to really help, not just symbolically, and you end up with hundreds of tons of added mass. Each extra ton needs more propulsion to accelerate it, more structure to hold it, and more fuel or power to move it. Then the rocket equation hits again. Your ship becomes heavier, so you need more fuel, which makes it heavier still, and so on. Very quickly, a theoretically safe design turns into something you simply cannot launch or push to high speed with any realistic engine. So if you cannot easily shield everything and the radiation keeps coming, which parts of your body fail first? And what does that look like over years, instead of months? We already see some of the effects in astronauts who spend 6 months to a year on the ISS, even though they are still partly protected by Earth's magnetic field. They show higher rates of cataracts in their eyes, changes in brain structure on scans, and clear shifts in immune system behaviour. These are at doses lower than what you would get in deep space, especially beyond the heliosphere. Over decades in interstellar space, your blood-producing bone marrow takes constant hits, which can reduce your ability to make new blood cells, weakening immunity and oxygen-carrying capacity. Your gut lining, which replaces cells quickly, suffers repeated damage. Your nervous system, including the brain, takes rare but serious hits from heavy nuclei that can cut through multiple cells in one track. Over time, this can lead to cognitive decline, memory issues, mood changes, and increased risk of strokes. This is not only about maybe you get cancer when you're old, it is about being at real risk of chronic fatigue, infections, organ damage, and possibly early dementia while you are still on the mission. When your entire job is to maintain a complex spacecraft, solve problems, and stay mentally stable, that kind of slow, constant damage is not a side issue. It is central to whether you can finish the mission at all. Up to now, most of this has been inside the sun's bubble, so what changes when you actually cross the heliopause and step into true interstellar space, where even that weak protection falls away? Inside the heliosphere, the sun's magnetic field and its outflow deflect a portion of the highest energy galactic cosmic rays. It is not a perfect shield, but it lowers the intensity that reaches you. Once you cross the heliopause, that shield quickly becomes irrelevant. You are now in the full raw flux of interstellar cosmic rays, without the sun's magnetic field buffering part of it. For the first humans to ever cross that line, the radiation levels they experience and the time they spend under that exposure will be in a regime no human body has ever endured. There is no long-term medical data for this environment. The best we have are robotic instruments and models. The odds are high that those first crews will hit health limits, not after a full planned mission, but somewhere along the way, as damage accumulates faster than their bodies and any medical tech on board can repair. And this is only one layer of stress. Radiation alone can push a body toward failure over years, but in an interstellar mission, it hits at the same time as microgravity damage, mechanical wear in the ship, and aging. So the next question is direct. If radiation is this bad, what happens when you combine it with the fact that your body was built for 1G and you take it away for decades? Your body evolved for one very specific environment, a planet pulling you down at 1G all the time. So what happens when you take that away? Not for 6 months like on the ISS, but for 20 or 30 years straight. In orbit today, where gravity is basically gone, astronauts start losing bone fast. In the weight-bearing parts of the skeleton, like hips and spine, they lose around 1 to 2% of bone density per month if they do not use countermeasures. Even with heavy exercise and special equipment, they still lose some. Muscles follow the same pattern. Without daily intense workouts, they shrink and weaken because the body decides it no longer needs that strength. This is on missions that last only 6 to 12 months. Now extend that to a deep space mission measured in decades, with limited equipment, limited medical care, and constant radiation on top. At that point, astronaut stops meaning elite athlete in space and starts meaning long-term patient in a moving clinic. Your bones become brittle, so a minor fall or a sudden jolt can cause fractures. Your muscles atrophy, so standing, lifting, or running, if you ever see gravity again, becomes a serious challenge, not a normal activity. Even if you never land anywhere, simple tasks like pulling yourself through the ship or dragging a heavy filter cartridge turn into exhausting work as you age in microgravity. If gravity is this central to your skeleton and muscles, what else does it quietly control? And what goes wrong when the direction down disappears for years? In microgravity, fluids in your body, blood and other liquids, are no longer pulled strongly toward your legs. They redistribute, moving toward your chest, head and face. Astronauts talk about puffy faces and thinner legs. That sounds harmless, but inside the skull, that extra fluid raises pressure around the brain and eyes. On the ISS, doctors have seen a cluster of problems linked to this. Optic nerves swelling, eyeballs flattening slightly, changes in vision that do not always fully reverse when people return to Earth. Put that same effect into a mission that lasts several years, maybe a decade or more, without a quick way back to a hospital. Your eyesight could slowly degrade from sharp corrected vision to something that no simple glasses fix cleanly. Reading screens, working on fine wiring, spotting small warning lights, all become harder and harder. For a crew that must constantly monitor complex systems and respond to alarms, losing visual clarity is not just an annoyance, it's a direct hit to safety. Eye surgery, advanced imaging, and specialist care are not available in the middle of interstellar space. If your eyes and brain are dealing with constant fluid pressure changes, what about the engine that keeps that fluid moving in the first place, your heart and blood vessels? How do they hold up when gravity has gone for good? On Earth, your heart is always pumping against gravity, pushing blood up to your brain when you stand and adjusting when you lie down or move quickly. In microgravity, that uphill fight almost disappears. At first, the heart has to manage the sudden fluid shift, but over time, when it realizes the workload is lower, the heart muscle can shrink. The vessels also change, some stiffen, some adjust diameter. Data from long ISS missions already show measurable changes in heart function and structure, and some increased risk of irregular heart rhythms. Now picture a 60 or 70-year-old crew member who has spent half a lifetime in these conditions. Their cardiovascular system has not just aged by the calendar, it has aged under a strange, constant stress pattern no human evolved for. When a crisis hits, maybe a fire in one module, a sudden leak, or a heavy repair job in a suit, that heart has to suddenly deliver. If it fails, there is no emergency room, no ambulance, no intensive care. A heart attack or a dangerous arrhythmia, which might be survivable on Earth, can easily become a final event in deep space. At this point, the obvious solution seems simple. If lack of gravity is wrecking you, why not bring gravity with you by spinning the ship and creating artificial gravity? Does that actually solve the problem, or does it create a whole new stack of engineering headaches? Artificial gravity by rotation is real physics, not science fiction. If you build a ring or a habitat with, say, a 100-meter radius, and you spin it at around 3 turns per minute, people at the rim will feel a force similar to 1G pulling them toward the outer wall. Walk on that wall and it feels like a floor. In principle, that could protect bones, muscles, and the cardiovascular system. But building such a structure is not simple. A 100-meter radius means a diameter of 200 meters, longer than 2 football fields end to end. It has to be strong enough to handle the constant tension from spinning, balanced enough that it does not wobble, and robust against impacts and material fatigue over decades. All that structure weighs a lot. Every extra kilogram has to be launched from Earth or built from material in space, then moved into interstellar trajectory. On top of that, you need bearings or connections between spinning and non-spinning parts, for things like antennas or propulsion systems that work better if they do not rotate. None of this is impossible in theory, but right now we do not have a human-rated, fully tested rotating habitat in space, not even on a small scale. So while artificial gravity could solve some medical problems, actually flying a huge, spinning habitat on the very first human mission out of the heliosphere means betting lives on a complex system with no long track record. If that system fails, suddenly or slowly, the crew is back in microgravity, but now older, more fragile, and already partly damaged. Take all of this together, bone loss, muscle wasting, fluid shifts, heart deconditioning, and the practical limits of building spin gravity. And then stretch it over 20 or 30 years, what do the likely causes of death actually look like for the first humans who try to go that far? The answer is blunt. They probably will not die from some exotic sci-fi disease. They will die from very ordinary medical events, pushed forward and made more likely by the space environment. A stroke caused by stressed blood vessels and a deconditioned heart. Heart failure in a body that has been living in microgravity and radiation for decades. A broken hip from a simple fall inside the ship. followed by complications and infection in a system with limited surgery and limited antibiotics. In normal life, these might strike in the 80s or 90s. In interstellar space, under constant radiation and unnatural gravity conditions, they could hit much earlier. And remember, all of this physical wear happens at the same time as the ship itself is aging, parts are breaking down, and supplies are being used up. So even if your body could somehow handle the environment, you still have to trust the vehicle to keep you alive for just as long. That leads straight to the next hard layer of this problem. If your own biology is struggling to last for decades in deep space, how do you keep the ship that keeps you alive from failing first? Right now, the longest running spacecraft we have, like Voyager and some Mars orbiters, are simple machines, low power, few moving parts, no humans on board. So what happens when you replace that with a ship that is basically a small city and then demand that it works for 30 to 50 years without real outside help? Your interstellar ship is not just a rocket, it is a stack of critical systems, life support, propulsion, power, cooling, navigation, communication, radiation shielding, food production, waste recycling. Every one of those systems is built from pumps, valves, filters, fans, sensors, circuit boards, software. In engineering, every component has a mean time to failure, an average time it will run before it breaks or drifts out of spec. On a mission that lasts 6 months, you can accept some risk and some wear. On a mission that lasts decades, those small probabilities stack up. Over 30 to 50 years of continuous operation, the chance that every key system stays inside its safe window is not just low, it trends towards zero. Think about the computers and phones you use. After 5 or 10 years, many of them are glitchy, slow, or dead. Now demand 40 years of nearly perfect performance in vacuum, under radiation, with temperature swings, and with human lives tied directly to the outcome. The risk is not that one part fails once. The risk is that, given enough time, everything that can fail eventually will, while you are still relying on it. If every system is slowly walking toward failure, how do you handle the one system you absolutely cannot afford to lose? The one that gives you air, water, and a stable environment when you have no resupply at all. On a long interstellar flight, you are not carrying infinite oxygen, water, or food. You are carrying some reserves, but mostly you are recycling. That means closed-loop life support. The air you breathe out, rich in carbon dioxide, has to be scrubbed and refreshed. The water you use for drinking, washing, and maybe plant growth has to be cleaned and reused. Solid waste needs to be broken down and fed back into the loop, either as nutrients for plants or as raw material for other processes. We already run a smaller version of this on the International Space Station. The environmental control and life support system takes in used air and water and returns it to a usable state. Even in low Earth orbit, with regular cargo flights bringing spare parts and filters, this system has issues: clogged lines, failing pumps, leaks, and sensors that drift. Crew members spend a large fraction of their time just keeping life support healthy. Now move that setup into interstellar space. No resupply ships, no quick return, no spare module you can dock. If a filter clogs, a pump seizes, a membrane tears, or bacterial growth gets out of control in one tank, you cannot throw it away and get a new one. You have to repair or rebuild it with what you have. Every small failure is either fixed by you, on site, or it quietly removes a function you rely on. Maybe your oxygen level starts to drift down. Maybe trace contaminants in the water slowly build up. Maybe humidity control fails and mold spreads. Life support becomes less like a machine and more like a fragile ecosystem, one that is always one bad day away from a step change in risk. While you are fighting to keep these internal systems stable, the ship's body itself is taking constant damage from outside. So what does that slow physical decay look like when you stretch it from years to decades? The hull of your ship cycles through large temperature swings. In direct sunlight, it can rise to around plus 100 degrees Celsius, about 212 degrees Fahrenheit, and in shadow it can drop toward minus 200 degrees Celsius, around minus 328 degrees Fahrenheit, depending on design and insulation. That repeated expansion and contraction, thousands and tens of thousands of times over decades, stresses materials, creates micro cracks, and weakens joints. At the same time, tiny dust grains and micrometeoroids, often moving at tens of kilometers per second, hit the hull. Each impact is small, but over years they pit surfaces, damage coatings, and erode exposed structures. Radiation from the sun and from galactic cosmic rays slowly breaks chemical bonds in plastics, rubbers, and sealants. Lubricants inside bearings and gearboxes can break down or outgas. Seals harden and lose flexibility. What starts as a perfectly tight pressure vessel slowly develops small leaks, stiff valves, and stiffening panels. On Earth, we deal with similar wear in aircraft, ships, and industrial plants by taking them offline, doing major overhauls, replacing large sections, or scrapping them. In interstellar space, you live inside the thing you're trying to keep from falling apart. You can patch, reinforce, and improvise, but you are fighting a one-way trend. The vehicle is aging faster than you can fully reset it. If everything is slowly wearing out, the obvious response is to bring spare parts for as much as possible. But how do you balance that against the brutal limits on mass, when every extra kilogram must be pushed to interstellar speeds? For a 40-year mission, you would like to have backups for almost every mission-critical component: extra pumps, valves, motors, seals, circuit boards, cables, filters, sensors, and control units. You might also want spare modules for complicated systems, like extra CO2 scrubber cartridges, or even entire replacement units that you can swap in. All of that adds mass. A single pump might weigh a few kilograms, a spare circuit board a few hundred grams, but multiply that by hundreds or thousands of parts, and suddenly you are adding tons of spares. The propulsion system does not care whether a kilogram is food, is shielding, or spare electronics. Every kilogram slows you down or demands more fuel. If you try to carry enough spares to cover almost every possible failure mode for 40 or 50 years, your ship can grow to a mass that is unrealistic to launch and accelerate. If you cut back to stay lighter, you accept a growing risk that some specific part will fail that you did not bring a backup for, or that you run out of certain spares before the mission ends. You are trapped between two hard options: carry so much mass that the mission becomes nearly impossible to launch, or travel light and accept that given long enough, something you cannot fix will break and stay broken. When that final unfixable failure arrives, it probably will not look like a dramatic explosion or a sudden cinematic disaster. So how does the likely end of such a mission actually play out step by step as the ship dies before you do? Most likely the ship's full functionality will fail gradually. First, small non-critical systems go, some sensors, some scientific instruments, comfort features like certain lights or exercise devices. You adapt. Then a more serious system takes a hit. Maybe the CO2 scrubbers become less efficient, and you have to ration activity to keep carbon dioxide levels safe. Maybe the water recycler breaks partly, so you have to accept lower water quality or stricter washing limits to stretch the remaining capability. Over time, one core system will cross a line. It might be life support, power, or thermal control. If power output drops too much, heaters and pumps cannot all run at once. If thermal control fails, parts of the ship can overheat or freeze. If life support crosses a maintenance point you cannot reach, carbon dioxide or humidity builds up or oxygen slowly declines. From the outside, the final causes of death might look boring: lack of oxygen, hypoxia leading to confusion, then unconsciousness, or dehydration as water becomes unsafe or impossible to recycle, or hypothermia if the ship can no longer remove waste heat correctly and your environment systems collapse. But behind each simple medical label is a clear, predictable engineering path that you could have plotted years before, watching graphs of performance trend downward, knowing that unless something changed, there was a date where survival would no longer be possible. And remember, all of this, the creeping failures and the constant patching, sits on top of your own aging in radiation and microgravity. So even if the ship somehow holds together, your body may not. Which raises the next hard question. If the vehicle that keeps you alive is always trying to fail, and your body is too, where do you get the power to run all these systems? And how do you get rid of the heat they produce while you are far beyond the reach of the sun? How do you run a small, closed world for decades when the main power source you use near Earth, the sun, drops away until it is almost useless? Near Earth, solar panels are great. At 1 astronomical unit, Earth's distance from the sun, the sunlight hitting a square meter is about 1,360 watts. With modern panels, you can turn a decent fraction of that into electricity. That is why satellites and the ISS spread big solar wings. They get steady, predictable power as long as they stay close to the sun. Move out to 10 astronomical units out near Saturn, and that sunlight drops by a factor of 100. Now each square meter gets only about 13 watts. Go out to around 120 astronomical units near the heliopause, and the sunlight is weaker by about a factor of 14,000 compared to Earth. At that point, 1 square meter of solar panel would get less than 1/10 of a watt. To power a serious ship that needs tens or hundreds of kilowatts, you would need solar panels with areas measured in many football fields, and they would still be fragile, hard to point and hard to protect. So for a true interstellar mission, solar power is effectively dead long before you leave the heliosphere. It fades out as a serious option while you're still in the outer solar system. Past that, you're flying in the dark, and you need another source of energy. If the sun can't power you anymore, what does and how complicated does that power plant have to be when it is the only thing keeping your world alive? The answer is nuclear power, your own artificial sun on board. Today, deep space probes use radioisotope thermoelectric generators, RTGs, which turn the heat from decaying plutonium into electricity. They are simple, with no moving parts, and very reliable, but they only produce a few hundred watts per unit, and their output slowly drops as the plutonium decays. A crewed interstellar ship is in a different league. Life support, communications, computers, pumps, heaters, maybe some form of electric propulsion or high-power tools, all of that adds up. You're not talking about hundreds of watts, you're talking about tens of thousands of watts, maybe hundreds of thousands, possibly into the megawatt range if propulsion is involved. That scale points to nuclear reactors, not just RTGs, actual reactors with control rods or similar systems, coolant loops, turbines or power conversion units, and safety structures. Each of those subsystems is another thing that can fail, leak or drift away from normal behaviour. You move from a few solid blocks of radioisotopes slowly fading to a complex, actively managed machine that must run without a major accident for decades, far from any help. Once you have a reactor or RTGs making heat and electricity, you face another basic problem. People often forget, in the middle of almost absolute cold, how do you get rid of the heat your own ship generates without an atmosphere to dump it into? On Earth, when a power plant or a car or your computer needs to get rid of heat, it usually dumps it into air or water, fluids that carry the energy away. In vacuum, there is no air to blow through a radiator. The only way to lose heat is by radiating it away as infrared light. The physics here is simple but brutal. The power you can radiate away depends on 2 main things: the surface area of your radiators and the fourth power of their temperature. That means if you want to get rid of more heat, you can make the radiators hotter, or you can make them bigger. There are limits to both. Make them too hot and your materials and fluids start to fail. Make them too big and you end up with vast thin panels stretching out from the ship, easy targets for micrometeoroids and hard to protect. For a ship throwing off megawatts of waste heat, which is likely if you run a powerful reactor and big life support systems, you might need hundreds or thousands of square meters of radiator surface. These radiators will sit there for decades, always slightly warm, always exposed. Small impacts can puncture them, coolant leaks can reduce performance, and radiation can slowly degrade their materials. Fixing a radiator problem in deep space is not as simple as sending up a repair crew for a satellite. It is you, in a suit, trying to patch or reroute a critical organ of your ship. As these power and cooling systems age, their performance will slide. So what does it really mean for day-to-day life on the ship when your watts start disappearing year after year? Every percent of power you lose forces choices. At first it is small. Maybe you dim lights, tighten temperature ranges, or run some experiments less often. Then you start cutting into more core functions. Pumps for water and air might run at lower speeds. Heating during sleep cycles might be reduced. Some modules may be kept cooler or warmer than is ideal to save power. If the reactor takes a more serious hit, or if your RTGs degrade faster than planned, your available energy could drop suddenly, not slowly. Then you have to decide in real time what matters more, keeping the air scrubbing system at full output, or keeping wastewater processing at maximum quality, or keeping certain heaters running to protect electronics. You may have to shut down communications bandwidth, slowing data and cutting contacts just to claw back watts for basic life support. For the first humans outside the heliosphere, the cause of death will not be space is cold in a vague sense. It will be specific. The air recycler does not have enough power to run its full cycle, or the water purifier cannot process fast enough, or the heaters in a critical section fail and pipes freeze and crack. The link between power and survival is direct. Even if the reactor itself holds together, the fuel inside your power sources is decaying over time. So how does the natural decline in nuclear output line up with the length of a human life on a deep mission? Take plutonium-238, a common fuel for RTGs. Its half-life is about 88 years, meaning that over that time the heat output, and thus the power from the generator, drops to about half of the starting value. On a mission that runs 40 to 60 years, the power from any RTG-style systems could fall by 20 to 30%, even if every other component is perfect. For a ship relying on both reactors and radioisotope units, this means your entire power budget is slowly shrinking while your crew is aging. The more years pass, the weaker both the people and the ship's heart become. Early in the mission, you have margin, extra watts, flexible operation. Late in the mission, when the crew is older, sicker, and the ship is more worn, you have less power to play with, fewer safety buffers, and less room for mistakes. At some point the curves cross, the power output falls below what is needed to run the minimum set of systems that keep humans alive in that environment. It may not be a sharp moment, but a creeping approach where every year feels tighter. Eventually the math wins, the crew and the power core fail in the same broad window of time, and there is no one and nothing left to correct the trend. And all of this still assumes that space itself stays quiet and empty around you. But it does not. The faster you go, and the longer you fly, the more every tiny particle in front of your ship turns into a physical threat. So once you have barely enough power to live, how do you survive when the thin gas and dust between the stars start hitting you like constant tiny bullets? How dangerous can a tiny dust grain really be when your ship is moving at a big fraction of light speed for decades? The answer is much worse than your instincts tell you, because at high speeds, the energy of even a speck of matter rises insanely fast. The energy of motion, kinetic energy, does not just scale with speed in a straight line, it scales with the speed multiplied by itself. If you double the speed, the energy jumps by 4 times. Go 10 times faster, the energy goes up by a factor of 100. Now plug in interstellar numbers. At 10% of light speed, around 30,000 kilometers per second, about 18.6 million miles per hour, a grain of sand with a mass of just 1 milligram, 1,000th of a gram, hits your hull with energy similar to a small hand grenade. That is from something you could barely see with your eyes. Even if you slow things down and talk about precursor missions at around 1,000 kilometers per second, about 2.2 million miles per hour, speeds that are already far beyond current human spacecraft, the picture is still ugly. At those speeds, a dust grain just a few micrometers across, smaller than a grain of talc powder, can carry impact energy in the same ballpark as a rifle bullet. You are not brushing harmless dust aside, you are flying into a stream of tiny high-velocity projectiles. If dust and gas are this dangerous at high speed, why do we call the space between stars a vacuum? And how empty is it really? once your ship starts ploughing through it for tens of years. The local interstellar medium, the stuff between stars in our part of the galaxy, is mostly hydrogen, with some helium and a small amount of heavier elements packed into dust grains. On average, there is about 1 atom of hydrogen in each cubic centimetre of space around here. That sounds like almost nothing. Even the best vacuum chambers on Earth usually have more particles per cubic centimetre than that. At slow speeds, for example the velocity of Voyager, that environment feels like perfect emptiness. The collisions with gas atoms are rare and low energy. Dust impacts happen, but they are infrequent and mostly manageable with modest shielding. At 10% of light speed that changes. Your forward hull is sweeping through an enormous volume of this thin gas every second. Each hydrogen atom that hits you slams into the ship with enough energy to knock electrons loose and create radiation. Together, they form a constant hail of atomic-scale bullets. Add in the occasional dust grain, and now you have sporadic shrapnel hits fired by nobody from nowhere, just because you are moving fast. This means the front of your ship is not just a wall moving through a vacuum, it is more like the first layer of armour in a constant, very high-speed sandblasting process. Every second, every minute, every year, the same surfaces take the hits. If particles are unavoidable, maybe you try to simply armour up. Can you really just stack shielding on the front of the ship and solve this? Or does that quickly run into the same mass and complexity traps as everything else in this mission? One common idea is a Whipple shield, named after the scientist who proposed it. Instead of one thick wall, you use several thinner layers spaced apart. When a fast particle or dust grain hits the first layer, it vaporizes or shatters, spreading into a cloud. That cloud then hits the next layer with lower intensity and so on, until very little gets through to the main hull. This works well for current spacecraft against micrometeoroids. For interstellar speeds, you scale that up. Maybe you add a sacrificial bumper at the front, a thick slab of material that will take the worst hits and slowly erode, protecting what is behind it. Some concepts add a cloud of gas or plasma ahead of the ship, generated by releasing gas or using electromagnetic fields, so that incoming particles are slowed or ionized before they reach hard structures. All of these solutions help, but none are free. Every extra layer of metal or composite, every tank of gas for a plasma shield, adds mass. That mass pushes your propulsion requirements up, which means more fuel, stronger engines, and more structural strength. The very act of trying to shield yourself against dust feeds back into the same rocket equation wall you already hit when talking about speed and shielding for radiation. You can protect the crew better, but you pay a heavy price in size and complexity. Suppose you do build strong shields and you avoid one knockout hit. What happens to your ship's front end over 30 or 40 years of constant bombardment, even if nothing catastrophic happens in a single moment? Over decades, cumulative erosion becomes a quiet but serious enemy. The forward surfaces, the nose of the ship, leading edges of shields, and any structures that stick out in the direction of travel will slowly ablate. Small craters merge into rough patches, protective coatings disappear, microscopic cracks grow under repeated thermal and mechanical stress. Electronics placed near the front, like star trackers, cameras, radar, and other sensors, take a steady dose of radiation and shock from near misses and small hits. Even if they are shielded, they are in a harsher environment than systems buried deep inside the hull. Over time, these instruments can start to fail one by one. Maybe a navigation camera dies, then a backup. Maybe a forward radar loses sensitivity. The ship can route around some of these losses using other sensors, but gradually the view ahead gets fuzzier. This means your sensor suite, the set of tools that tell you where you are and what is in front of you, can go partially blind long before the crew does. You might still be alive, breathing and thinking clearly, but the ship will not see space as sharply as it did at launch. Course corrections become less precise. Early warning for larger debris gets weaker. The mission continues, but with growing uncertainty. So far this sounds like a slow grind, but when you fly for tens of years through a thin fog of dust, what are the chances that you hit something just big enough? In just the wrong way, that it jumps straight past slow erosion and puts you into an emergency you can't control. On a 30 to 50-year mission at high speed, the combined odds of hitting at least one slightly larger grain, maybe millimeter scale or bigger, are not something you can safely ignore. A particle that size, moving at 10% of light speed, has an impact energy that can punch deep into shielding and structure. Even at lower but still extreme speeds, a hit like that can penetrate multiple layers. The result does not need to be a giant explosion. It can be a narrow hole that lets air leak from one module, or a crack in a key coolant line, or a sudden short in an important cable bundle. The crew might have warning alarms, pressure sensors, or impact detectors. They can race to seal a compartment, patch a puncture, or reroute around the damaged systems. But you can only do that so many times, with limited supplies, tools, and physical stamina. It is very plausible that the first human interstellar vehicles will not end in one dramatic visible event, but in a series of impacts and failures that gradually cut the ship's interior into isolated pockets, or force the shutdown of more and more systems. You end up with slow leaks, darkened sections, offline instruments, and a crew always one failure behind. At some point, the chain of damage runs ahead of what you can repair. Air, water, or power escapes faster than you can stop it, and the mission ends, not because you hit a planet or a star, but because a slightly larger grain, in the wrong place, finally tipped a system you had been holding together for years. And remember, dust is just one part of what lives between the stars. The rest of the interstellar medium, the thin gas, the plasma, and the magnetic fields, is also interacting with your ship the whole time. So if the solid particles alone can slowly tear your vehicle apart, what does that same environment do to your electric charge, your instruments, and your navigation when you're completely surrounded by it? When you think of the space between stars, you probably picture pure emptiness, but the reality is a thin, active gas that never stops touching your ship. And over billions of kilometers, even that almost nothing adds up in ways that can mess with everything you rely on. The interstellar medium, the stuff between stars, is mostly hydrogen and helium. The average density near our Sun is about one particle in each cubic centimetre of space. That is far emptier than the best vacuum chambers on Earth, where there are still thousands or millions of particles in the same volume. But now scale that up. Your ship is not travelling through a few centimetres. It is flying through distances measured in trillions of kilometres, trillions of miles, for decades at high speed. At those scales, you are not just in empty space, you're ploughing through a very thin plasma, a gas where many atoms are ionized, meaning they have lost or gained electrons and now carry electric charge. This plasma does not care about your mission. It does not care that you need stable power, clean signals, and precise navigation. It simply reacts to your motion and your electrical and magnetic fields, and those reactions can slowly bend your path and stress your systems. If the gas is ionized and your ship is charged and moving, what does that do to your hull and electronics over years, when there is no one to fly up and fix a single fried board? As your ship moves through this ionized gas, particles from the plasma hit the hull, stick, or strip off electrons. Different parts of the ship, with different materials and shapes, can charge up in slightly different ways. Without careful design, some areas can end up at higher voltages than others. Over time, you can build up enough charge that it suddenly discharges, jumping as a small arc between surfaces. We already see this in Earth orbit. Satellites can accumulate charge from space plasma and sunlight, then discharge suddenly, causing glitches or even permanent damage in electronics. Engineers fight this with conductive coatings, grounding, and devices called plasma contactors that gently bleed charge away. Now push that problem into interstellar space. Speeds are higher, exposure times are much longer, and the plasma environment is less well understood. Your hull can develop unexpected charge patterns. A discharge might happen deep inside a cable harness or inside a sensor. It can scramble a computer, corrupt stored data, or break a critical control board. Each event is random from your point of view. You may not even see a clear cause, just weird resets or dead instruments. To avoid this, your ship has to be built with highly conductive outer layers, controlled pathways for charge to escape, and active systems that monitor and neutralize buildup. That adds complexity. More things that have to work right for decades. If they drift out of spec, the ship slowly turns into a big moving capacitor, waiting for the wrong moment to discharge in the wrong place. If the plasma is messing with your charge, what about the galaxy's magnetic fields and your navigation, when tiny forces acting for years can shift a carefully aimed path by trillions of kilometers? The Milky Way is threaded with weak magnetic fields. They are nothing like the strong magnets you see in labs, but they are spread over huge distances, a charged, moving object, like your ship with its own electric currents, feels forces when it cuts through these fields. The currents in your power systems, in your plasma shields if you have them, and in any charged exhaust you throw out the back, all interact with the external magnetic environment. Each effect is tiny. In a short mission, you could safely ignore them, but over light-year scales and decades of flight, those small nudges can add up. The result is a slow, constant set of perturbations on your trajectory. Left uncorrected, they can shift your aim, changing a carefully planned flyby of a star system into a miss by hundreds of billions of kilometers. To stay on course, you have to measure your position and velocity precisely, compare them to the mission plan, and make regular corrections using thrusters or other propulsion methods. Every correction uses propellant or steals momentum from your main drive system. That means you either carry extra fuel just for navigation, adding mass, or you accept that your course will slowly drift if that fuel runs low. Drift too much, and your mission to Proxima becomes a mission that passes far outside the target system, with no way to brake or turn back. You are then just another object on a long, empty trajectory, with no practical way to rebuild the original goal. And all of this starts right where you cross the boundary of the heliosphere. So what is actually waiting for you at that boundary, and just beyond it, where we only have a few robotic data points to go on? When you leave the heliosphere, you do not step into a calm, uniform plasma. You pass through the sun's wake, the region where the solar wind and the interstellar medium fought and mixed. Data from Voyager showed that this boundary is not smooth. There are shock waves, regions of turbulence, and unexpected changes in particle density and magnetic field direction. The heliopause is more like a messy transition zone than a clean surface. There can be layers where fields point in different directions or where particle densities spike. Once outside, you're in the interstellar medium, but still inside the sun's broader wake. The exact structure of that wake is not fully mapped. We have only a couple of paths through it at specific times, with instruments that were not designed for crude mission planning. This means the first human ship moving through this region will, in a very literal sense, be a moving experiment in plasma physics. You're the test particles. You will see unexpected currents, waves, and field changes. These might add noise to your instruments, cause drifts in your power systems, or create extra drag and heating on parts of your hull. You'll be trying to understand the environment at the same time as you're trying to survive in it. As the years pass and your models and reality keep drifting apart, what does that do to the crew's confidence and to the mission's ability to stay on top of the risks? At launch, you leave with detailed models of the plasma environment, the dust distribution, the average magnetic field, and how your ship is supposed to behave. Over time, you collect data, compare it to predictions, and update your plans. But every time there is a surprise, a higher than expected current on a cable, an unexpected drag signal, a strange reading from a particle detector, you have to ask, is this a one-off, or a sign that your basic understanding is wrong? Each unexpected effect forces you to use more power, more propellant, or more shielding in ways you did not originally budget for. Maybe you have to run plasma contactors more often, spending power. Maybe you need more course corrections than planned. Maybe some forward sensors degrade faster than your models predicted, leaving you with less information than you expected this far out. After 10, 20, 30 years of this, you can easily end up in a situation where the ship you're actually flying is no longer the ship that was on under paper. Its mass distribution has changed, its power output is lower, its shielding is thinner in some spots, and its instruments do not perfectly match the design assumptions. The environment also is not exactly what your launch day models said. You're operating in a growing gap between plan and reality. At some point you have to accept a hard truth. Maybe the interstellar space you're actually in is more hostile, more chaotic, or just more different than the one you designed for. You cannot turn around. You do not have the fuel or the time to go back to the heliosphere. You can only push on with shrinking resources and rising uncertainty. And all through this, there is another quiet threat building, not outside the ship, but inside it, in the people. Hardware can only be as effective as the minds operating it. So if the environment keeps surprising you and the systems keep wearing down, how long before the crew itself starts to crack under isolation, delay, and the knowledge that they will never see any world again? You've seen how the environment, the ship, and your body all try to break you over decades. Now add one more layer, your mind, and the tiny culture trapped with you. Because none of this works if the people running the ship stop functioning. On the ISS, astronauts are only about 400 kilometers, around 250 miles, above Earth. They see the planet under them every day. They talk to mission control with only a small delay, almost real time. If something critical breaks, cargo ships can bring new parts. If someone gets very sick, there is at least a path home within months. That is already stressful, and it already pushes human psychology. On an interstellar ship, you are not hundreds of kilometers up, you are billions of kilometers out, then trillions, far beyond any planet. Communication delay stops being seconds, it becomes hours, then days. At 1 light hour away, a radio signal takes 1 hour to reach Earth, and 1 hour for a reply to come back. At 1 light day, it is 24 hours each way. You cannot have conversations anymore. You send a message, you wait, and later you get an answer to a question you might not even care about by that point. It feels less like talking to people and more like sending logs into a mailbox that rarely answers. With that kind of delay, Earth stops being an active partner in your life and becomes more like a distant archive, a place you report to, not a place you live with. If tensions rise on the ship, if someone is close to a breakdown, there is no real-time counselor, no quick intervention, just delayed advice and canned protocols. If this much isolation is built in from day one, the obvious question is, what do we already know from tough, long missions in extreme places, even when they are still on or near Earth? We have data from Antarctic winter overs, where small crews live in remote stations, cut off for months by weather and darkness. We have results from Mars simulation habitats, where volunteers live in closed environments for many months. We have decades of experience from ISIS expeditions. In all these cases, even with the knowledge that the mission will end and Earth is right there, people show higher rates of depression, sleep disruption, anxiety, and interpersonal conflict. Small annoyances grow. The way someone chews, the way they leave tools out, the style of leadership, all of that can turn into serious long-term friction. On Earth, or in low orbit, you can rotate people out, change teams, send in new supplies, bring in fresh medical support. On a 20-year interstellar mission, you do not. The small group you launch with is, in practice, the group you have for life. That means every argument, every grating habit is not something you can just walk away from. There is no taking a weekend off, no stepping outside for a real break. You share a few tens or maybe hundreds of meters of pressurized volume, the same air, the same routines, and the same faces for years. If a relationship collapses, you still have to work with that person day after day to avoid dying together. If living with the same people forever is hard, then you have to decide who those people are over decades. Do you freeze a single crew in time, or do you bring in children who never agreed to this mission in the first place? There are two basic models. One, you send a single generation. They launch in their 20s or 30s, and if the mission lasts 40 or 50 years, they die in their 60s, 70s or 80s, still in transit. No children on board, no new crew, just the original team aging together. Two, you build a generation ship with enough space and resources for people to have children, who will grow up and eventually take over operations. The single-generation plan avoids some social complexity, but it means your crew spends its entire adult life in one vehicle under constant stress, watching their own bodies fail. Motivation tends to drop with age, especially when rewards are abstract and distant. The generation ship plan spreads the workload, but creates another problem. The kids never chose to leave the solar system. They wake up into a mission decided by strangers, with a destination they will probably never see. In both cases, by the later years of the mission, you have people whose priorities and beliefs have drifted away from the launch day plan. Some crew might stay committed, others might resent the mission, or simply become apathetic. You cannot force enthusiasm out of them by command when there is nowhere to send them if they refuse. If they decide that strict adherence to some original scientific goal no longer matters, they can in practice change course, cut off communication, or reassign resources. You have no external authority that can send a replacement or remove them. Deep down, underneath all the daily routines and maintenance, there is another pressure that never goes away, the knowledge that you personally are never arriving anywhere. How does that shape your mind over years? From the moment you see the mission profile, you know the basics. You will not stand on another world. You will not orbit another star and then take a lander down to a new planet. At best, if you're in a very optimistic scenario, you might fly past another system at a distance and take data. Realistically, for the first human mission beyond the heliosphere, you will not even get that near. You're not going to Proxima Centauri, you're just moving humanity's physical reach a little farther out from the sun. That changes the meaning of your work. You're not a colonist, you're not a pioneer who will plant a physical flag on solid ground. You're a data source, a test pilot, a caretaker of instruments sending back measurements that other people will use after you are gone. Some personalities can handle that. They can treat every repair, every experiment, every log entry as meaningful because it pushes knowledge forward. But many people struggle when the rewards are abstract, delayed by decades and not visible to them. When the ship is cold, something is broken again, your joints hurt and you're missing a real sky, is easy to ask, what is the point? That question does not vanish, it grows. If enough crew members stop seeing the point, they might start quietly cutting corners, skipping maintenance, or simply refusing high-risk repairs. The mission then degrades not just because of physics, but because of choice. While all this is happening inside the crew, the culture, the shared stories and values that hold them together is changing too. And it is changing in an extremely small and closed space. What does that look like after 10, 20, 30 years? Inside a world ship, everything cultural happens in a tiny volume, maybe a few tens of meters across between walls, airlocks, and bulkheads. All art, music, jokes, arguments, and traditions come from the same small group and they are digital archives. Over time, people reinterpret old stories about Earth. New myths form around the launch, the mission controllers, even around the machinery that keeps them alive. Children, if there are any, grow up with no direct experience of planets, skies, or oceans. For them, those are distant tales. Because the system is closed, there is almost no fresh input. New ideas only arrive in the form of delayed messages from Earth, which, as the light time delay grows, start to feel less relevant. A movie or news broadcast that left Earth 10 years ago and reaches you now may not match your reality at all. The crew might slowly stop paying attention to Earth culture, focusing instead on their own, tightly looped version. By the time the first humans to leave the solar system reach the later part of their lives, they may not see themselves as explorers in the way their mission planners did. They might see themselves as members of a unique, separate micro-society, with its own priorities, rules, and sense of purpose, or lack of it. They could die not as representatives of Earth pushing outward, but as founders of a small drifting civilization that has cut most of its psychological ties with the planet that launched it. And while all of this is unfolding in their heads, one robotic mission has already been living the die far from home script for decades, without feelings, without fear, just raw engineering and slow decay. So what can that machine Voyager actually tell you about what it really looks like when a mission keeps going into the dark, while its power, instruments, and contact with home all fade away. One real spacecraft has already done a dry run of what it looks like to head out into the dark, keep working while everything ages, and then slowly fade. That spacecraft is Voyager. Voyager 1 and Voyager 2 launched in 1977, using technology from the 1970s. Their main computers have less processing power than a cheap pocket calculator today. Memory is measured in kilobytes, not gigabytes. Yet with that hardware, Voyager 1 is now more than 150 astronomical units from the Sun, over 22 billion kilometers away, about 14 billion miles, moving at around 17 kilometers per second, about 38,000 miles per hour. And it is still sending back data. That makes Voyager 1 our only real working example of hardware operating at interstellar distances. It has crossed the heliopause. It has flown beyond the planets, beyond most of the Sun's protective bubble. When we talk about what a machine looks like after decades in deep space, we are not guessing from zero, we are looking at Voyager and scaling up. If a simple robot can do this, the natural question is, why can't we just copy the idea at human scale? And what does Voyager's slow decline actually look like when you zoom in on its power and instruments? Voyager gets its power from radioisotope generators. These are solid blocks that turn the heat from decaying plutonium into electricity. They are reliable and have no moving parts, but the energy they produce drops over time as the plutonium decays. When Voyager launched, the power budget was enough to run a full suite of instruments, heaters, and communication gear. Decade by decade, the output has gone down. Engineers have had to make hard choices. They have turned off non-essential instruments one by one, shutting down cameras, some detectors, and heaters in less critical areas. They do this to keep a handful of key systems alive: the transmitter, basic computers, and a small set of sensors that still return valuable data. If you think of the spacecraft as a nervous system, you're watching it go dark piece by piece. First it stops seeing in certain colours of radiation, then it loses other senses. The core can still talk, but with fewer and fewer inputs. For a human ship, the same pattern would show up in a much more brutal way. Instead of switching off a particle detector, you would be shutting down a greenhouse or a lab or a spare life support loop just to keep the main air system and heaters powered. As Voyager goes farther, keeping contact becomes harder too. So what does talking to a machine that far away really look like in terms of signal strength and data, and how does that compare to what a human mission would face? By now, Voyager's radio signal arrives at Earth extremely weak. The power level, by the time it hits our big ground antennas, is far, far smaller than the output of a watch battery, spread over the area of a huge dish. To pull usable information out of that whisper, we need massive antennas and very sensitive receivers. Even then, the data rate has dropped compared to what it was when Voyager was near the planets. As distance increases, signal strength drops with the square of the distance. Double the distance, and the signal gets 4 times weaker. To keep talking, you have to slow down how fast you send bits, and you have to use more of those bits for error correction. That means less actual science data, less content per unit time. A human interstellar ship would go through the same curve. For a while early in the mission, communication would be rich with high data rates, video, large files, even near real-time conversations while still in the inner system. Then, as the distance grows to tens, hundreds, thousands of astronomical units, the available data rate shrinks. Eventually you cannot send full logs or detailed medical records. You cut down to compressed summaries, then maybe just health pings and occasional bursts of science. At some point you might hit a stage where the ship can still send a carrier signal, but you can no longer decode meaningful content reliably. That leads to a hard truth. A human interstellar mission may very well end in a way that Earth never fully sees. The final days or weeks could be poorly recorded, or not recorded at all, simply because the radio link has broken down too far. From Earth's point of view, one day the pings just stop. On top of fading power and weaker signals, Voyager has also shown that deep space throws up problems we did not predict in detail. So what kind of surprises has it already given us? And what does that say about crewed missions? Over the years, Voyager has had glitches in its attitude control, issues with memory, unexpected behaviours in its instruments, and anomalies in data as it crossed new boundaries like the termination shock and the heliopause. Engineers on the ground have had to dig into old documentation, rewrite software, reroute commands, and sometimes use parts of the spacecraft in ways that were never intended, just to keep it working. All of this has been done by large expert teams on Earth, with full access to simulation tools, test hardware and backup systems, and with the ability to think for weeks or months before sending a new command. They are not under life support pressure. If a workaround fails, nobody dies. On a human ship, the crew becomes that engineering team, but with much fewer people, less hardware, and no way to wait weeks in full safety if the fault is threatening a key system. They will be trying to repair pumps, rewrite control software, and jury rig replacements, while also dealing with their own health, isolation, and aging. And they will be doing it all on hardware that by mid-mission is already well beyond its original design life. If you put all of this together, power decay, systems being turned off, fragile communication, and surprise failures, the pattern should look familiar. So how close is Voyager's path to the path you can expect for a human interstellar pioneer? Voyager today is a stripped-down version of its launch self. It has fading power, a shrinking set of working instruments, and a radio link that takes many hours for signals to travel. It is moving into deeper night, with no real target it will ever reach in human timescales. At some point, its power will drop below the level needed to run the transmitter and basic heaters. The electronics will cool and the last signal will fade. After that, it will keep coasting, dark and silent, effectively dead as a mission, but still physically there. A human interstellar mission is the same shape, just scaled up and made much crueler. Your power source fades. You start turning off non-essential gear. Communication gets weaker and slower. Hardware failures appear more often. You patch what you can, shut down what you cannot save, and watch the ship's capabilities shrink. You keep going because there is no alternative direction to go. The one huge difference is that Voyager does not care. It does not feel fear when its instruments go dark. It does not feel loneliness when its data rate drops. A human crew will understand exactly what is happening as their world shrinks, as systems die, and as messages from Earth turn from real-time support into delayed history. And after seeing how hard it is just to keep a simple robot limping along in the outer darkness, the next question hits with full force. If getting a tiny uncrewed probe this far was already at the edge of what we could do, what does that say about the propulsion we would need to push a huge, fragile, crewed ship to the speeds and distances we have been talking about? You've seen what happens to the ship and your body if you spend decades in deep space, but all of that still assumes you can even reach deep space at a useful speed. So what actually fails when people say, we'll just go faster? Start with what we already use, chemical rockets. The big launchers today, the ones that put payloads into orbit, can give you a change in speed of a few kilometers per second from their upper stages, roughly 3 to 9 kilometers per second, about 7,000 to 20,000 miles per hour. To send probes out of the solar system, we stack these burns with gravity assists, using giant planets like Jupiter to steal a bit of their orbital speed. That is how Voyager, New Horizons, and others got their high exit speeds. But all of this happens with relatively small, uncrewed probes. A human ship is much bigger and more fragile. You cannot throw it a few hundred kilometers above Jupiter at insane speeds, with razor-thin margins, without adding a lot of risk. And the core physics of chemical rockets does not change. Their exhaust speed stays around a few kilometers per second. You can add more boosters, more stages, more complexity, but you are fighting steeply rising mass and cost for only modest gains in final speed. To hit even 1% of light speed, around 3,000 kilometers per second, when your engine can only throw exhaust out the back at around 4 kilometers per second, the math crushes you. You would need a ridiculous amount of fuel, far more than is practical. You do not get to 10% of light speed, 0.1 C, by strapping on more boosters. You just burn more fuel for a ship that is still crawling by interstellar standards. If chemical rockets are already at the edge, you might turn to more efficient engines, like ion and electric drives, So can those finally give you the missing speed, or do they run into a different wall? Ion drives and other electric propulsion systems are very efficient with propellant. Instead of exhaust speeds of a few kilometers per second, they can throw ions out the back at tens of kilometers per second, in some cases more. That means each kilogram of propellant gives you a lot more push over time, which is great. But the trade-off is thrust. An ion engine pushes very gently. It can run for months or years, continuously and slowly add speed, which is perfect for small probes that don't care about time. The Dawn spacecraft, for example, used ion drives to spiral out and visit multiple asteroids. Its thrust was comparable to the weight of a sheet of paper in your hand, tiny. Scale that to a crewed ship weighing thousands of tons, and the same thrust barely moves the needle. You can add more ion engines, but each one needs electrical power. To get enough total thrust to accelerate a huge ship to a big fraction of light speed in a reasonable time, you would need enormous power sources, likely nuclear reactors, and big radiators to dump waste heat. At that point, your ship becomes even heavier, which means the same engines do less for your overall speed. Ion and electric drives are like very efficient tortoises, great at nudging a light probe over long periods, bad at punching a massive crewed vehicle into the relativistic speed range you need to make interstellar travel work within a human lifetime. So if chemical is too weak and ion is too slow, you look at the next step, nuclear and fusion concepts. But do these finally break the pattern, or do they just move the problem to a more dangerous level? Nuclear thermal rockets heat a propellant, usually hydrogen, with a reactor, and throw it out the back. That can roughly double or triple exhaust speed compared to chemical, which gives you much better performance for the same fuel mass. For missions inside the solar system, that is a big win. But for interstellar, even 3 times better than chemical is not enough to get you to 0.1 C with a practical mass ratio. Then there are nuclear pulse concepts, like the old Project Orion idea, where you literally detonate a series of nuclear bombs behind a strong pusher plate and ride the blasts. On paper, these can give huge changes in speed, because each explosion is very energetic, but they come with major problems: engineering, safety, and the fact that you are repeatedly slamming a structure with nuclear shockwaves and asking it to survive for decades. Fusion drives, where you fuse light atoms like hydrogen into heavier ones and tap the released energy, look even better on paper. So do antimatter. Concepts. Their theoretical exhaust speeds are high enough to make interstellar flight within a lifetime at least numerically possible. But right now, fusion for propulsion is still a research topic, and antimatter production is tiny and extremely expensive. We do not have working space-ready fusion or antimatter or engines. Even if we build a fusion prototype sometime this century, the first human mission beyond the heliosphere will not be using a polished, perfectly reliable star drive. It will be using an early, cautious, under-tested version of that tech, or a hybrid system. That means lower performance than the ideal numbers, more safety margins, and probably lower top speed than what the most optimistic papers show. If onboard engines all hit hard limits, maybe you try a different trick, pushing the ship from the outside with light or microwaves, but does that really work for a human craft, or only for tiny probes? Beamed energy propulsion tries to solve the fuel problem by not carrying all the energy source on board. Instead, you build giant laser or microwave arrays near your home system. They shine on a sail attached to your spacecraft, pushing it with the momentum of light. For very light probes, just grams to kilograms, this can in principle get you to 10 or 20% of light speed. Projects like Breakthrough Starshot are studying exactly this kind of thing for ultra-small probes. Now scale up to a crewed ship that weighs thousands of tons. The power needed from the lasers or microwaves increases in proportion. You go from needing, say, tens or hundreds of gigawatts for small probes, to needing power outputs that start to approach or exceed the entire electrical production of modern nations, focused into beams held on target over long distances through space. You also need huge optics or phased arrays spread over kilometers, maybe thousands of kilometers, to keep the beam focused on the sail as the ship accelerates away. Building that infrastructure in space is a massive project in its own right. The first humans to leave the solar system are very unlikely to wait until we have multi-thousand-kilometre laser arrays and perfect massive sails. They will go much earlier, with less developed systems, which means lower speeds and higher risk. Even if you somehow get a working beamed system, you still face the other big problem you've already seen. As you push the speed up, dust and radiation hit harder. So where is the real operating window where you can move fast enough to leave the heliosphere, but not so fast that space itself kills you even quicker? As speed rises, the energy in every impact and every radiation event scales up sharply. Dust grains that are irritating at 100 km per second become dangerous at 1,000 km per second and catastrophic at 30,000 km per second, 0.1 C. The gas of the interstellar medium becomes a source of constant particle radiation, because in your frame those atoms are slamming into your ship at extreme speeds. Your shielding mass, your cooling systems, and your structural strength all have to grow to cope. That means there is a narrow, ugly band of speeds where you can do something meaningful. You can go fast enough to leave the heliosphere in a human timescale, maybe in a few decades, but still too slow to reach another star within one normal human lifetime. In that band, you still suffer most of the long-term damage from radiation, microgravity, and mechanical wear, but you do not get the science fiction upside of arriving at a new world while you are still alive. Everything we know today points to this harsh conclusion. The first human interstellar mission will probably sit in that window, fast enough to get beyond the heliosphere and deep into the Oort cloud, while some of the original crew are still alive. Not fast enough to reach the nearest star, or any real destination, before those same people die. Speed alone will not save them. So if propulsion cannot make you effectively immortal, or let you skip decades of travel, the next idea people reach for is to change the passenger instead of the engine, to hack biology, slow metabolism, or even put people into some kind of sleep. But when you look at real science, not science fiction, how far do those tricks actually go before they hit the same brick wall, and you still die in space just a bit later? After you see how hard it is to push a normal human body through decades of deep space, the next instinct is simple. Don't send a normal body, change it, freeze it, slow it down, or repair it faster. The problem is, when you look at actual biology and medicine, those fixes only move the wall a little. They don't remove it. Cryosleep is the classic science fiction answer. Put people into suspended animation, fly for decades, then wake them up fresh at the other end. Right now, that is still basically fiction. We can cool some small animals into a torpor-like state and bring them back. We can preserve single organs, like a heart or a kidney, at low temperatures for hours, sometimes a bit more, and then transplant them. But a whole human body is much more complex. When you freeze water inside cells, ice crystals form and rip membranes apart. Even if you use cryoprotective chemicals to reduce ice, those chemicals can be toxic in their own ways. Cooling and rewarming a big complex object like a human evenly is extremely hard. Some regions freeze faster, some thaw slower, and that creates mechanical and chemical stress. On top of that, fully shutting down metabolism has effects on every system, hormones, brain function, immune responses that we barely understand over days, never mind years. So right now, putting a human into true suspended animation for decades, then safely reviving them with full brain function and no major organ damage, is far beyond anything we can actually do in a clinic. On an interstellar ship, there is no hospital backup. If your sleep tech fails halfway through, you do not get a second try. If full freezing is out of reach, maybe you can aim lower and just slow the body down, induce torpor instead of full cryosleep. Does that get you any closer to surviving the trip? There are early studies in animals, and some work in emergency medicine, looking at ways to induce a hibernation-like state. This might involve controlled cooling, drugs that change how cells use energy, or carefully adjusting gases in the blood. In some mammals, it is possible to lower body temperature a bit and reduce metabolic rate, making the animal use less oxygen and energy for a short time. For spaceflight, that might buy you some advantages. A crew in torpor for a few days or weeks at a time could use less food and water, and maybe be slightly less sensitive to certain kinds of radiation damage while their cells are less active. But that is a very small gain compared to what you would need for interstellar travel. Lower metabolism for a few days or weeks is not the same as turn off almost everything for 40 years. Even if we get safe reversible torpor working for, say, a month at a time, you still have to cycle people in and out, you still have to handle long-term radiation, and aging still continues, just a bit slower. You're not skipping the journey. You're just making parts of it feel shorter subjectively, while the universe keeps the real clock running. If slowing the body down is limited, the next move people reach for is to change the body itself at the genetic level. Can't you just build a radiation-tough, bone-loss-resistant human and fly that instead? We already know a lot of genes involved in things like DNA repair, radiation resistance, and bone density. We see them in animal studies with mice and fruit flies. We see extreme examples in organisms like tardigrades, tiny creatures that can survive vacuum and radiation far better than humans, thanks to special proteins and DNA repair mechanisms. In theory, you could add some of those traits to humans. You could try to boost DNA repair pathways, strengthen bones, or make cells more resistant to damage from cosmic rays. You might even try altering how the immune system responds to long-term stress, but in practice that means germline gene editing, so the changes are built into every cell of the body and passed on to children. Doing that on a small, closed crew is a huge ethical and practical risk. Any mistake, any unforeseen side effect spreads through the whole population. Maybe the change that helps with radiation also raises the risk of autoimmune disease. Maybe boosting bone density increases the chance of dangerous clots. You cannot test these changes over 60 years on Earth before you launch. You would be turning the first interstellar crew into a live experiment, with no backup population, no way to roll back, and no guarantee that the space-optimized human is stable or healthy across a full lifetime. Even if you could improve baseline biology a bit, bodies still wear out. So maybe the answer is to repair and replace parts aggressively with high-end biomedicine and cybernetics. Can that hold you together for the full mission? You could absolutely pack the ship with advanced medical tools, organ-on-chip systems to grow tissues, stem cell therapies to regenerate damaged bone marrow or heart muscle, 3D bioprinters to print skin grafts, cartilage, maybe even simple organs, cybernetic implants to replace failing joints, improve vision, or support damaged nerves. In theory, you can treat some diseases, delay others, and compensate for lost function with machines. But every one of these tools has requirements. They need consumables, growth media, reagents, energy, clean labs, and spare parts. The devices themselves can fail. Software needs updating. The crew has to stay trained to use them, and that means training new people as older doctors and technicians age or die. Over decades, stocks of rare chemicals and specialized components run down. Machines designed for 10 or 15 years of use creep into their third or fourth decade. At the same time, the patients are not living in a safe environment. They are living in microgravity under radiation, with chronic stress, and with limited diet and limited physical variety. So each new therapy is being asked to patch a body that is already more damaged than a typical patient on Earth. The medical toolkit shrinks while the damage load grows. When you add all of this up, cryosleep, torpor, gene edits, and advanced repairs, it is clear that they can push the line out a bit, but they cannot erase it. So what does that actually mean for how long you can function in interstellar space? If everything goes well, these tricks might stretch your effective working life. Instead of being able to handle the mission from, say, age 25 to 70, maybe you can stay functional into your 80s or even 90s. Maybe torpor cycles reduce total radiation dose a bit. Maybe gene tweaks slow bone loss. Maybe stem cell treatments rebuild some of the damage from radiation and microgravity. But none of this makes you immortal. It does not let you shrug off high-energy cosmic rays or decades of tiny hits to your brain and organs. It does not stop your chromosomes from shortening, your proteins from misfolding, or your tissues from stiffening. All these interventions do is buy you time, and time is exactly what deep space uses to kill you. So the first humans to leave the solar system will still die in space, most likely of things we would label natural causes on a death certificate: heart failure, stroke, cancer, infection, organ collapse. The difference is that those causes will be pushed forward, twisted, and complicated by radiation, microgravity, isolation, and long-term wear. You do not become a star traveller who outlasts the journey. You become a human who fights a losing battle just slightly longer. And while all of this is happening, your path through space still has to be aimed and tracked with high precision, and your link to Earth still has to carry your story back. So if your body and ship are both trying to fail, what happens when your navigation and communication systems, the only tools that tell you where you are and who is still listening, also start to slide away over light-year distances? You've seen how hard it is just to stay alive on the ship, but all of that still assumes one thing: that you know where you are going and that you can stay pointed at it for decades. Over interstellar distances, even that basic assumption starts to break. At launch, your trajectory is defined by a very precise angle. If that angle is off by a tiny amount, the missed distance years later is not tiny at all. Take 1 arc-second of error, that's 1/3600th of a degree, a shift so small most people could never notice it by eye. Over a trip of about 4 light years, that tiny angle translates to a miss of around 0.02 light years. In distance, that is over 200 billion kilometers, roughly 125 billion miles. That's not a small navigation error, that's blowing past the entire target system. To correct that, you need to fire thrusters or use some exotic momentum control. Each correction burns propellant or eats into whatever method you use for fine control. Early in the mission, you have margin, you can afford to trim your course regularly, but every burn empties tanks a little more. At some point you are forced to choose: save fuel for late mission corrections or use it now to stay perfectly on track. Eventually, the budget runs out. From then on, any drift is permanent. You are locked into whatever line your ship is on when the last correction ends. Even if you launch perfectly and correct smartly, the stars themselves don't sit still for you. So how do you keep your map accurate when the sky you're flying into is slowly changing shape as you move? Stars move relative to each other. Over decades, their position shifts slightly in the sky. By the time you've been flying for 20, 30, 40 years, the pattern of bright points ahead is not exactly what you saw at launch. Our star catalogues already account for this motion, called proper motion, and for parallax effects. But your navigation is not just reading a book, it is matching live sensor data to predictions. Add more complications. At high speeds, the light from stars appears slightly shifted toward your direction of travel, a relativistic aberration effect. The interstellar medium, the thin gas and plasma, can bend and scatter radio signals from background sources. Your own ship's sensors, cameras, star trackers and telescopes are slowly degrading from radiation and small impacts. So your onboard nav system is always trying to align 3 things: a star map that evolves, sensors that are getting noisier, and a trajectory that depends on how well your last corrections actually performed. If your sensors lose resolution, or if some star trackers fail, your map can slowly unhook from reality. You think you are pointed a certain way, but the real sky and your real path are starting to drift apart. While your navigation is fighting to stay accurate, your communication link to Earth is stretching out. So how much help can mission control actually give you when every message has to cross light hour or light day gaps? At 100 astronomical units from the Sun, a bit beyond where Voyager is now, a radio signal takes about 14 hours for a round trip, 7 hours each way. At 1,000 astronomical units, that round trip is close to a week. Once you are in true interstellar space, the delay goes to weeks or even months. That means mission control cannot fly the ship in any direct sense. They cannot see a problem and send an immediate fix. By the time advice arrives, the situation on board has already changed. So Earth's role shrinks. Early on, controllers can give detailed step-by-step instructions. Later, they can only send broader guidelines and software updates. In a real emergency, the crew cannot wait for the permission or a checklist. They are on their own, making life-critical decisions with whatever they know at that moment. The farther you go, the more support turns into historical background. On top of the time delay, the strength of the radio signal is also decaying, so what happens to the actual amount of information you can send and receive as the distance keeps growing? Signal strength drops with distance in a very simple way. If you double how far you are from Earth, the power received at the antenna on the ground becomes 4 times weaker. Triple the distance and it is 9 times weaker. With fixed antennas on your ship and fixed transmitter power, your data rates have to drop over time just to keep a lock on the signal. To keep messages readable, you devote more of each transmission to error correction, codes that help Earth reconstruct the original data, even if some bits are lost or flipped. That overhead eats into your usable data stream. In the early years, you can send rich telemetry, science images, video, long logs, and personal messages. Later, you may be limited to compressed status summaries and small data packets. There is a scenario where your ship's radio can still send a carrier signal, a simple tone that says "I exist," but cannot reliably carry complex data. In that case, your detailed logs, the personal diaries of the crew, high-resolution science, all of it, might sit on onboard storage and never get fully transmitted before power or link quality fails. The true record of what happened becomes something only the people on that ship ever know, and that assumes your navigation and pointing hardware stays healthy. But as parts fail, what happens when you start losing the very tools that tell you your position and aim your antennas? To know where you are and to keep your main antenna pointed at Earth, you rely on star trackers, gyroscopes, reaction wheels, or control thrusters, and sometimes external references like pulsars. Over decades, those components wear out. Reaction wheels can seize, thrusters can get clogged or lose efficiency. Star trackers can be blinded or degraded by radiation damage. Gyros can drift. At first, you work around each failure. You switch to backup sensors, recalibrate, change software to ignore bad data. But backups are finite. When a key set of sensors is gone and there is no further replacement, you are stuck with rough estimates. Your position in space gains larger and larger uncertainty bars. Maybe you think you're within 1 million kilometers of a certain path, then 10 million, then 100 million, then more. Your antenna pointing also gets less precise. A high-gain dish has a narrow beam. If your aim drifts outside that beam, Earth's receivers see nothing. In the end, you may reach a point where you cannot say exactly where you are. Not because you hit something dramatic, but because too many small pieces of the nav and comm system died. You won't be approaching Proxima Centauri in a neat trajectory graphic. You will be a tiny, untrackable speck in a volume of space so huge that your coordinates are guesses. From Earth's point of view, sometime after launch, you're a well-tracked mission, then a distant probe, then a faint whisper, then a missing signal that never quite came back. From your point of view, on the ship, you're alive in a place no one can see clearly, on a path no one can fully predict, with no way home and no real hope of arrival. And that brings up the final unavoidable question. If the physics, engineering, and biology together make it almost certain that the first humans to leave the solar system will die in space, never reaching another star, what does it mean, ethically, to send them anyway? And where is the line between exploration and simply using people up for data? How do you justify sending people on a mission where the best realistic outcome is that they all die far from any human world, and the main thing that comes back is data? That is the ethical core of the first interstellar flight, and it is not a normal risk calculation. There will be volunteers, we already know that. People have signed up for the proposed one-way Mars missions. People already choose dangerous jobs, from test pilots to deep-sea divers to frontline medics. So it is easy to say, if they agree, it's fine. But here the question is, how informed can that agreement really be? You're asking someone to sign up for a mission with no historical precedent. No one has ever lived in deep space outside the heliosphere for decades. No one has ever dealt with that mix of radiation, isolation, aging, and slow ship failure. The failure modes are not fully known. Even experts are still arguing about long-term radiation damage and deep space plasma behavior. On top of that, you're asking for a very specific kind of death. Not just you might die, but you will die, and you will die where no body recovery, no funeral, no marker is possible. There is no emergency return, no rescue ship staged behind you. When you sign, you are not only accepting personal risk, you are closing the door on every normal human ritual around death. Consent under those conditions has to be brutally clear, with no soft marketing, no hidden downside. Right now, regular spaceflight already accepts non-zero odds of losing a crew, so where exactly does an interstellar mission cross from extreme risk into something else? In the early space shuttle era, internal estimates for loss of crew were on the order of 1 in 100 flights, sometimes worse. For Apollo, the risk of not returning from the moon was high enough that contingency speeches were written in case astronauts died on the surface. Everyone involved knew there was a real chance of failure. But the missions were designed and sold as survivable round-trip flights. The goal was to bring people back, and death was the bad outcome. An interstellar mission with current and near-term physics flips that. The realistic expectation is that the mission will kill you. The only open questions are when and whether the information you send back before that happens is worth it. The probability of eventual crew loss is not a fraction, it is basically 100%. From a strict engineering point of view, you're trading guaranteed human deaths for probable knowledge gains. That is a different ethical category. You're no longer minimizing the chance of loss of crew, you're accepting it as built-in, and then arguing about whether the payoff justifies a mission profile where no participant survives to see any direct benefit. To make that easier to sell, there is a strong temptation to lean on the hero story, but what happens when you use that narrative to cover up how asymmetric the deal really is? We praise explorers like Magellan, Shackleton, Gagarin, Armstrong. We turn them into symbols of courage, and we tell their stories as proof that progress requires risk. It is very easy to wrap a one-way interstellar mission in the same language, to call the crew the new Magellans of the galaxy, and talk about glory and legacy. But look at the balance. The crew takes all of the physical risk, and all of the psychological cost. They age in a tin can, far from any world, knowing they will die there. The benefits, the new physics, new engineering lessons, new data about interstellar space, mostly flow to future generations and to institutions on Earth, agencies, companies, governments, universities. The crew will never walk in a city built with the tech their mission inspired. They will never see a working interstellar colony, or even a successful second-generation mission. They see one ship from inside until their eyes close. Calling them heroes can be accurate, but it can also be used to downplay that the trade is deeply one-sided. If we lean too hard on glory and not hard enough on the cold details, we are not honouring them. We are using their image to make ourselves feel better. Then there is the hard social question. When you pick the people who go, who actually gets put on that list? Oh, and whose bodies does the system decide are acceptable to lose in deep space? Selection will not be random. You will want people with excellent health, strong skills in engineering, medicine, biology, navigation, psychology. You will want people with stable mental profiles, low risk of violent behaviour and high resilience. You will also want people who can handle isolation and delayed rewards. All of this costs money, training, screening, long preparation. Rich nations and powerful organisations are the ones who can fund a mission like this. That means they control who gets a chance to volunteer, who passes the filters, and whose name stays on the shortlist. Existing inequalities will shape that pool. Some groups may be overrepresented as ideal candidates. Others may be excluded quietly. There is also the risk that people from poorer backgrounds, or with fewer options, feel pressured to volunteer because this is framed as the highest possible form of service or escape, even if they do not fully grasp the technical risks. Sending people to certain death in interstellar space is not just a scientific act, it is also a social one. It forces us to look at how we value individual lives versus collective futures, and whether that value changes depending on which individuals we're talking about. Underneath all of this is one final blunt problem. Where is the line between an acceptable if extreme mission and something that looks more like ritualized sacrifice, and who decides where that line is? Some ethicists will argue that such a mission can be moral, if and only if volunteers understand the situation clearly, are free from coercion, and the knowledge gained is enormous, reshaping what humanity can do next. In that view, the crew is similar to soldiers volunteering for an extremely dangerous mission, or early test pilots flying experimental jets with high crash rates. The difference in scale and distance is big, but the basic logic is the same. Informed adults choosing to take a known risk for a perceived greater good. Others will say that once you know every participant will die far from any chance of rescue, with the mission plan built around that fact, you have crossed a line. You're not primarily trying to protect them and failing, you are planning around their deaths from the start. That starts to look less like exploration and more like a sacrifice ritual wrapped in scientific language, especially if symbolic value and national prestige are used to sell it. The first humans to leave the solar system, if they go under anything like the conditions we have described, will sit exactly on that line. They will be part explorers, part experimental subjects, part symbols. We as a species will have to decide whether we are honest enough to name what we are asking of them, and whether we are willing to carry that moral weight when their ship finally goes dark. And after all of this, one question is still left hanging. If the first humans to leave the solar system are almost guaranteed to die in space with no arrival, no return, and no rescue, why does their mission still matter at all for the rest of us? And what does their death actually change for the future of our species? So after all this, after radiation, broken bodies, failing ships, and certain death, why does sending the first humans beyond the solar system still matter? Because it marks a hard change in what your species is. Right now, you're an animal that evolved on one planet, under one sky with one sun. You learned how to split atoms, build rockets, and send tiny probes past the heliopause, but that still keeps you in the category of a planetary civilization with long arms. The solar system feels huge, but the Milky Way is about 100,000 light-years across. The entire volume you've explored so far is a pinprick in that scale. When a human crew crosses the heliopause on purpose in a vehicle built for that job, that's the first deliberate step from we live around one planet to we are testing if we can live in the galaxy at all. Even if those people die in the dark, the simple fact that humans once lived and operated outside the sun's magnetic bubble proves the step is physically possible. It's a switch from theory and robots to we actually did it, with real human bodies. That physical presence is only half the story though. The real legacy is what they send back before everything fails. Every number they transmit becomes a permanent part of how we design whatever comes next. Think about what that data actually looks like. Year-by-year radiation levels, inside and outside different shielding setups. Detailed logs of how their life support systems really performed over 5, 10, 20, 30 years. Records of how their vision changed, how their bones thinned, how their hearts and brains handled decades in microgravity and interstellar radiation. Exact failure timelines for pumps, filters, radiators, reactors. Real breakdown chains, not guesses. Those measurements will rewrite textbooks and design manuals. Future spacecraft will set thicker shields here, thinner there, not based on guesses, but on the exact points where the first crew started to get sick. Future mission planners will set new limits for acceptable doses, safe durations, redundancy levels, and crew size, because they have a complete data set of one mission that pushed everything until it broke. Their bodies will stop. Their data won't. In that sense, they become part of the software of every later interstellar design. Their deaths turn into hard numbers that define what's safe and what isn't for people who launch a century later. Once you put actual humans outside the heliosphere, something else shifts quietly but permanently, your sense of what home means. Before that, home is Earth first, then maybe the inner planets, maybe the whole solar system in a loose way. Deep space is out there. After a human has lived for years beyond the heliopause, home is no longer just a ball of rock and one magnetosphere. Home becomes where humans are, even if that's a pressurized cylinder 150 astronomical units from the sun, 22 billion kilometers out, about 14 billion miles. You now have a moving shell of human presence around the star, not just fixed points on planets. Over time, that shell can thicken. Other missions can push outward behind them, maybe with better shielding, better drives, and shorter timescales. Maybe no one reaches another star in a single lifetime for a long time, but mentally, the line has moved from "we live near Earth" to "we can place human life almost anywhere around this star, even outside its magnetic protection for a while." That is a different civilization shape. To make their mission possible in the first place, you have to build infrastructure that outlives them, and that same infrastructure becomes the starting point for everything afterwards, even though they never see it mature. You'll need huge power systems, probably in orbit, to build and test reactors and maybe beamed propulsion. You'll need orbital shipyards that can assemble and maintain structures larger than any rocket fairing. You'll need fully closed-loop life support that can run for decades without resupply. You'll need fast, automated manufacture of spare parts in space. Those tools do not disappear when the first interstellar crew dies. They stay in your near-space economy. Later missions to the outer planets, asteroid mining, large telescopes, even routine deep space habitats can all run on that same backbone. The first crew never walks through a thriving interplanetary network, but they are the reason it gets built in time. So you end up with this final hard truth. The first humans to leave the solar system will almost certainly die in space. They will be killed by time, radiation, mechanical decay, psychological pressure, or just normal aging in a place with no hospital and no way back. They won't reach another sun. They won't step on another Earth. But their deaths mark a transition point. Before them, humanity is tied to one star's inner bubble. After them, humanity is a process moving outward generation by generation, ship by ship, learning from each failure, adding each data set to the stack. Bodies and vehicles will keep being lost. Knowledge and capability will stack up. You don't survive the trip, your civilization does. And the first people who die in the dark beyond the heliopause are the ones who prove that your species is willing to push past every natural limit it was born with, even when the payoff is so far in the future that they won't live to see it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.